Hello and welcome to the 643rd VJug session, ish, maybe something more like 50-ish. Welcome to the session. This is our first session in July. It was an absolutely fun-packed June with conferences, and we had 5 VJug sessions in total then. So we're having a much more chilled out 2 VJug sessions, much more normal 2 VJug sessions in July. And first up, joining myself and Oleg. Hey, Oleg. Big wave from
Hi, people.
Hey. Joining myself and Oleg is Mr. Christopher Beatty. How are you doing, Chris?
I'm very well, Simon. How are you?
I'm very good, thanks. And you're joining us from London, I take it.
London, yeah.
I know you're very well travelled these days around the world. Pretty much always travelling in June, weren't you?
Yeah, pretty much. Had a few days at home.
Awesome. So today, Chris, you're going to be talking to us about Cassandra.
I am.
Awesome. Looking forward to that. So before we jump into that, let me quickly click share screen. Share my entire screen. And let's jump to this. So this is the virtual jug. Obviously, the virtual Java user group. If you're just watching on YouTube, you're welcome to watch directly on virtualjug.com. And we're going to be talking about Cassandra. So the title is why would I use a distributed database like Apache Cassandra? The speaker today, as I mentioned, was Christopher Beatty, and you're welcome to follow Christopher on Twitter at @chbeatty. And just to mention that the Virtual Jug is sponsored by Zero Turnaround and has a media partner of Rebel Labs, and Rebel Labs will does a write-up of all Virtual Jug sessions. So you'll see the Chris's Cassandra session, hopefully written up this week, and you can see that on Rebel Labs' website. So a little word about Zero Turnaround. Zero Turnaround is a company all about developers. They create revolutionary developer tools. 2 of which are JRebel and XRebel, and you can grab free, fully functional trials of both JRebel and XRebel from zeroturnaround.com. JRebel is a tool that allows you to reload your Java code changes instantly in your runtime, and XRebel is a lightweight Java profiler that allows you to run profiling on your Java applications, your web apps, at development time. For those of you watching the Virtual Jug live, you can interact with us on our IRC channel, which you can either do directly through virtualjug.com, or you can go to a Freenode channel pound or hash Virtual Jug. Please do share the group session. We're still kind of in startup phase of our Virtual Jug community, so please do share that with your friends, mum, dad, pets, anyone you want to. And you can help us grow. If you have any feedback, please do send that directly to the @virtualjug or the @sjmaple Twitter handle, which is myself. And you should all follow @sjmaple because it's one of the best Twitter handles I've ever seen. Without further ado, let's hand over to Mr. Chris Beatty. He's going to talk about Cassandra. So let me.
One second, Christopher. Before you start and before Simon starts showing your screen, we have a minor trouble on the virtualjug.com website because the YouTube video, which should be us right now, is still the previous session. Not sure how to update that. Simon, maybe you can comment on that, or just fix the issue.
Almost certainly my fault. Let me click update.
Yeah, that'd be lovely.
Right, let's see if
the RC chat is also kind of getting a bit nervous about, like, where's Christopher? We want Christopher, and yeah, the website is updated now. So I think we could be starting any second now. So. Yep, the website is up.
Is that working? So in short, for those of you who have missed everything I said, welcome Christopher. Welcome Christopher to the Virtual Jug session. For those of you who are watching this on replay, this is just a kind of catch up in your memory. Welcome Christopher to the Virtual Jug. Chris is going to be talking about Cassandra. and everyone should go and buy JRebel and XRebel. That's pretty much it.
And follow Simon.
And follow me at SJ Maple. Yeah. Thanks very much for that. That was cool. So Christopher, over to you.
Thank you very much. I'll just share my screen. So shout loudly if it doesn't work.
I can see your second screen actually. I think there we go. Perfect.
Perfect. All right. Well, it's pretty exciting to be on the virtual jug. I know I've seen some great sessions here, so hopefully I don't let you down with this one. If you're going to get the most out of this session, if you haven't worked with a database like Cassandra before, I think it's best to start to think about the last outage you had. The last time you were called in the middle of the night because one of your applications went down, or one of your databases went down, or there was a problem with the network. Or perhaps the last time you had to replace a system due to the fundamental architectural issues, it just wouldn't scale with your customer base. Those are the types of things we're going to be talking about today. So if you've got an example from your job or your day job, fresh in your mind, you'll get the most out of this. A more specific agenda is going to be, first we're going to talk about the NoSQL space and what do we actually mean by a NoSQL database, because that space has got pretty huge now, and people love using it as a marketing term. And there are all sorts of things in there like caches and search tools and actually some databases as well. But as application developers, we need to make sure that we don't just assume something is a suitable database just because it's been branded as NoSQL. The next thing I want to talk about is why on earth would we actually want to use a distributed database? And by a distributed database, I basically just mean running your whatever data store you're using on multiple machines, because this is going to add complexity. So you've got to make sure that there's a reason you're doing this, and you're not just doing it because you're doing some CV-driven development. Once we've kind of convinced ourselves we have a problem, or we'll be able to recognize a problem that would require a distributed database, let's go into how we actually do that. I'm not just going to talk about Cassandra's architecture, I'll talk about the other databases which I've had experience with. So we'll talk about master-slave and sharding, but then we're going to end up with a deep dive into exactly how Cassandra does it. Because if you're used to things like Oracle and DB2 and Mongo, it's very, very different how Cassandra does it. And I'll just point out something really, really obvious, that Cassandra is an open source project. It's hosted by Apache. It's not owned by my employer, DataStax. And if you're going to start to use a truly open source project, I would definitely recommend that you get involved in the open source community. So jump on the IRC, get on the Jira, raise bugs, comment on new features. Even if you don't do it on the server side, make sure you do it on the driver side, because I probably got to the point where I hate embedding software inside my application, jars, that aren't open source. I want to see exactly what's going on. And if you're used to systems like Oracle or IBM products, you're not used to being able to give feedback and then get response and then it be incorporated into the next version in the matter of weeks. But if you're using an open source project, that's actually possible. So before we jump into all that, I'll just give you a 1-minute introduction. You don't really care who I am. I'm just trying to convince you that I know a lot about Cassandra and have a lot of experience with it. So for the last 2.5, 3 years, I've been building systems pretty much exclusively with Apache Cassandra. Also a bit of Oracle, a bit of Mongo. And over the last 6 months, I've actually moved to the company which contributes the majority of the code. That's DataStax. And now I spend most of my time contributing to open source technology in and around the Cassandra ecosystem. I work on a library called Stub Cassandra, and in addition to that, I work as an advocate. So I go around conferences and talk and do things like this. If you're actually based in London, I encourage you to reach out, and if you're thinking about using a system like Cassandra, because I'm more than happy to come and help you, no charge whatsoever. It's just part of my job to help out Apache Cassandra users. But that's enough about me. Let's get into the interesting technology. So what do we actually mean by NoSQL? Okay, I know there's various versions of the acronym. Maybe it's not only SQL, maybe it actually means NoSQL, but it's basically just everything else. And I think as technologists, we need to make sure we understand the technology that we're going to use. We're not just using it because it's gone on Reddit or they've read an industry benchmark. So we need to understand everything in this space. We've got a lot of caches in this space. So Redis, Hazelcast, they're pretty awesome tools, but they're not databases. But if you read some blog articles, like one I read recently was benchmarking Redis versus Cassandra. Now, to me, that's absolutely ridiculous. You're basically, just because they're both branded with NoSQL, we're comparing like a durable database with a cache, which is crazy to me. We've also got lots of search tools. Most of them are Lucene-based, and we've got awesome projects like Apache Solr, and we've got Elasticsearch. And most projects that you work on can be enhanced by actually using a search tool, because if you've got human interaction with your application, then typically humans just want to search around. They don't know quite what they're looking for. But again, they're not databases. And then we actually have some databases in the NoSQL space. So, and the way I categorize a database is it cares about durability above all else. So it's actually going to save your data. It can be your source of truth within your application. And they typically have things like commit logs, and you're going to be able to you're going to be able to configure how often it f-syncs to disk. So you actually know that this thing that you've stored into a database is actually going to be stored. That's not the case for typical search systems and caching systems. So when you're evaluating technology in this space, just make sure you're picking the right one. A thing which I often do to then further narrow down the type of database I want to use for my application is whether my data set is greater than memory or less than memory of the servers I'm using. Because some technologies in this space work very, very well as long as your data set fits in the cluster's memory, and some of them don't. Cassandra very much works in the space where we expect the data set to be vastly greater than the memory of your cluster. The next thing I like to think about is whether I intend to do ad hoc querying or whether I intend to denormalize. Now, that could be a silly thing to say, because of course you want to be able to do ad hoc querying. We're so used to storing things in third normal form and being able to decide later how to read it. But if you've built systems and you've tried to scale these queries in a large relational database, you'll have hit scalability bottlenecks. You'll have done things like remove constraints. You'll have merged tables to get performance out of these databases. So you just need to think, is your data set size going to allow you to use a system which offers you ad hoc querying? Cassandra, again, is on the right here. It's going to encourage you to denormalize from the get-go so you can actually scale your system, regardless of how many servers you want to throw at it. And the last thing is basically aiming for availability or high availability. For me, there is a huge difference between high availability and trying to aim for no downtime. And the architecture that you pick, or the technologies that you pick, their architecture will dictate whether you can actually aim for no downtime. Now, you've got to do this for your entire technology stack, but we're going to see the two different types, two different general ways in which databases work. One is going to encourage consistency, one is going to encourage no downtime. So once we've got all of that in our heads, the next thing we need to decide is whether we want to pick a technology which is actually going to run on multiple servers. Why would we actually want to distribute our database? Because this isn't necessarily a good idea. Our database, for me, is the thing which I can use to be a lazy application developer. I can leave all of my consistency to this wonderful database. It's going to give me, a linear order of operations. It's going to handle my transactions. I'm going to use, if you've ever tried to use XA transactions on a queuing system in a database, okay, it might not perform, but it very much allows you to easily reason about your application. As soon as you go into a distributed database, you've got so many more things to think about. But there are reasons we have to do it. The first obvious one from my point of view is the fact that your data just doesn't fit on a single machine. Now, yes, we can buy very expensive machines and with huge network attached storage, and we can probably always fit it on a single machine if we're willing to spend many, many millions. But a lot of us want to work on more commodity hardware, or we want to run on services like Amazon Web Services or Google Compute Engine, where the actual machine size is quite limited, or we're just not millionaires. The next item, I think, is throughput. And you can further divide this into, say, read and write, because you can get to a point where any single server is not going to give you the read and write capacity that you need. So you want to scale for that reason. Sometimes it could be read, sometimes it could be write, or sometimes it could be total data size. I think they're kind of the 3 dimensions of scale when it comes to databases. Then we move on to things which are more relevant for fault tolerance. So do we want to be able to keep our application online when we have hardware failure? This could be single servers. It could even be individual disks or CPUs. Perhaps it could be entire racks. You know, a rack in your data center or an availability zone in Amazon goes down. Do you want to be able to handle that, you know, without downtime? Or it could be your entire data center because a hurricane hits your data center. Which leads naturally on to whether you want to run your database in multi-data centers. Now, I say most people wouldn't even think of deploying their application to multiple data centers until they have an outage, which was completely because they lost service of one of their data centers. Now, typically these are not glamorous things like hurricanes or tornadoes. Normally it's something to do with the network or the ISP or the power supply. But you can't really build an always-on system if you're going to stick inside a single data center. So many people will deploy either active-passive or active-active across 2 data centers in each region of the world. If you haven't come across these phrases, active and passive, all I mean by these is, let's say I've got 2 data centers in New York in case there's a hurricane. Am I using them both during the happy time? Or am I just using a single one with the idea that I will fail over if there's some catastrophe and my data center stops working? Probably more realistic, the better thing to think of from an application developer, though, is actually data locality with the users of your application. So if you've got a website which has global appeal, you are not going to service your customers from Australia from a data center in the United Kingdom. That will give a terrible user experience, just the latency involved. And if you're going to run across multiple data centers, it's implied that you need to run your database across multiple data centers. And all of this leads you to the ability, if you try hard enough, to do releases without downtime as well. If you can patch your operating systems of all your servers, if you can roll out new versions of your applications, or roll out new versions of your database without having any downtime, then that's great for your customers. A couple of real-life examples of kind of extreme real-life examples of some of these things is a couple of Cassandra's biggest users. So if you've got an iPhone, you're typically using Cassandra pretty much every day. And they definitely fall into the category of their data is not going to fit on a single machine. Now, we're not all going to work on systems where we need, tens of thousands of database servers and individual database instances of over 1,000 nodes. But we will start to run across multiple servers as soon as we're doing anything, over the web, and we've got a lot of traffic from our users. From a fault tolerance and downtime point of view, then the experts in this field, I think, are Netflix. So if you can see the tweet I've just put up there, that's from Christos, which is one of the lead cloud engineers at Netflix. If you use AWS, you'll probably be aware that last year they decided to do what they called the reboot apocalypse. Well, they didn't call it that. People called it that on Twitter afterward. So they basically decided that they needed to reboot pretty much every machine. I think it was to patch a hypervisor. Now, if you're running a traditional technology here, this would fill you with dread. You'd be scared to your bone. You're going to reboot all of your database servers, an entire continent. That doesn't sound like fun. But the tweet there is just showing that Netflix actually had all of their Cassandra instances rebooted, and a number of them didn't even come back, which can happen in Amazon, which I'm sure a lot of us are aware. And they had zero downtime. If you've come across the Chaos Monkey, which seems to be mentioned a lot in talks and conferences these days. Chaos Monkey is Netflix's service which goes around and knocks down servers in production to make sure that their application developers, like us, are building fault-tolerant applications. They didn't previously run this on their databases, But when this came about, there's a whole blog, a whole article on the Netflix tech blog about how they started to run the Chaos Monkey on their database servers when they realized Amazon were going to do this. It's definitely worth a read. So if you fall into any of these categories, then how are we actually going to run our database? How are we actually going to scale our database? Now, maybe you don't, and there are many use cases out there in the world where a single instance of Postgres or Oracle or MySQL is still going to be your best bet. But let's say we do need to scale. Now, you'll probably be aware that you get either vertical or horizontal scaling. Vertical scaling is just where we continue to buy a bigger and bigger server. So we essentially scale via money. If you have a IBM rep or an Oracle rep in your organization, they like this. They like you to buy more of their hardware and run their server with more and more cores. And these IBM guys typically come and point at you and say, you should buy more and more of our software. Though I think this particular IBMer has left, so we won't blame him.
Although we were both in the same boat there, right, Chris?
We were. I was working for IBM as well at the same time. But hey, there's nothing wrong with that. It's just not going to be the topic. And it's great that Simon is still watching. That was a test. And we're actually not going to talk about vertical scaling here. We're going to talk about horizontal scaling. So this is the ability to run our piece of software, either our application or our database server, on many, many smaller machines rather than one large machine. And this is reasonably hard at the application level. You need to put effort into developing your application so it's stateless, and thus you can run it on multiple servers with a load balancer in front. But it's even harder at the database level. The database, even though it's probably the most important and complex thing inside your organization, is often the thing which is not made the most HA, highly available, just because it's harder. So how are we actually going to run a database across multiple servers? Before we talk about how Cassandra does it, let's see how we've all been doing it for many, many years. So you're probably going to come across terminology like primary, secondary, or master-slave. So if you have an existing database technology, then chances are this is how it's going to run across multiple servers. So you have a master. That takes in all of your reads and writes to start off with. But you decide you want to scale or you want to achieve some fault tolerance if that master goes down. So what typically happens is they add on a feature which will asynchronously replicate to other servers. So you're doing an entire new copy of your data, but on different servers. Now, there are some technologies that will do this synchronously. So when you do a transaction inside your database, it's actually waiting for the other two servers to acknowledge it. Now, this is great from a consistency point of view, but pretty terrible from an availability point of view. Because that means if any of the slaves are down, or the network connectivity between the master and the slave is down, then you lose availability. You stop being able to take in writes or do reads. Now, what has this gained us? Well, it's allowed us to scale reads because we can now use our clients. They can now talk to the slaves, and they can actually we can maybe increase our read throughput by a magnitude here of 3. So now we've got 3 servers to achieve reads from rather than just 1. And of course, we've already got some eventual consistency here. If a server writes to the master and there's asynchronous replication going on in the background, then there's no guarantee that if he reads, it's going to actually see the latest value. Now, of course, you can add some sticky sessions in here, and you can make it synchronous replication, but you're going to affect uptime here. What we haven't done here, though, is scale writes. We've still only got one node that the writes go to, and we haven't scaled total data size. So here, for me, I think we've only scaled one out of the 3 things that we need to scale. But if the only thing you need to do is scale reads, then this is a good solution. Another way just to scale reads is, of course, to run a caching system like Redis on top of your relational data store, or whichever technology you're using under the covers. The additional benefit that this gives us is that we've got a level of fault tolerance. We can handle the master going down now, and we can fall over to one of the other nodes and allow it to become the master. Now, depending on your technology that you're using, this might be automated. So there might be some failure detector going on in here. It could be an external service like Zookeeper. It could be an external like a cluster manager, or it could be built in. Now, if you've ever studied failure detection, distributed systems, this typically will not happen instantly. This will take some time. So you're inherently going to have some downtime with this type of architecture. It might not be much, but it's not going to be always on. The second thing is to decide which one becomes the master. So again, a topic of research is master election in a distributed system, like a consensus algorithm. That again takes some time. So we've inherently got some downtime here, but that could be okay. But what we need to do next is scale writes, because as we've said, all we've done here is scale reads and give us a little bit extra fault tolerance. So how do we scale writes in this system? Well, you've probably come across this term, and if you haven't, you're going to now, and it's sharding. A lot of operations people, if you're listening, you've probably now turned off because sharding is your worst nightmare. But that's typically what we do with these systems. We basically run multiple copies of this master-slave architecture, and depending on which system you're using, the sharding might be handled at the database level. So you might actually have a separate server running, which is working out which data belongs in which shard, or it could be happen at the application level. So let's say you've got 3 million customers. You might at your application level decide that 0 to 1 million are on the first shard, the next million are on the middle shard, and then the final million are on the other shard. So we've achieved all three types of scalability here. We've done reads, we've done writes now because we have 3 masters that we can write to, and we've scaled total data size. So we can now have more data because we're not fully replicated. This gets you into an interesting conundrum though, because these technologies, some of their best features are being able to do ad hoc querying. Now, why can they do ad hoc querying? Well, if you think about it, they can do it because all of your data is on a single server. So you don't really need to do a lot of network hops to be able to satisfy queries. So if you think of how a auto increment works in a relational database, think how you would implement that. The invariant there is that that every ID is unique, and if you ask for the next one, you get the next one. So if it's at 6, you get 7. If it's at 7, you get 8. You could imagine implementing this on a single server database. You could imagine implementing it in Java with, say, an atomic long or something like that. But how do you do it once you've done this? Because what you've done here is you've spread your problem across many servers, but most of the people who are interacting with them, the application developers, they're not used to having to deal with the lack of global invariance. So how do we manage unique primary keys across a sharded system? Well, either you don't, and you have unique primary keys within the server, or you have a process which is going to talk to all of them, and it's actually going to be slower the more shards you add. So I think inherently any type of global invariant across shards isn't a scalable feature. So what you typically have to do is stick to local invariants within a shard, and then things go really well. But the problem then is you lose the ad hoc querying, you lose the ability to do joins, etc. So you typically have to change your data model as and when you start to shard. So as and when your business is going well or your application gets lots and lots of throughput, you're having to change a lot of things, which is never a good thing. When we start to talk about some of these trade-offs, it's only a matter of time until someone brings up cap theorem. Now, a lot of people do not like, and maybe myself included, I'd be interested in your opinions afterward, don't like classifying databases with cap theorem. They think, oh, it's not descriptive enough. Databases don't really fall into just one. And I completely agree with you. But what cap theorem is really useful for is for having a discussion about where a technology is aiming to be. If you haven't come across cap theorem or you can't quite remember it from university, it is essentially the theorem which says you've got 3 properties of a distributed system and you can select 2 out of 3. A lot of the time people don't really understand the definitions of the 3 though. For consistency, what the cap theorem talks about is linearizable consistency, a globally defined order of events, not consistency as I might talk about it when we're talking about Cassandra. The other is availability. Now, what that really means in this theorem is for all of the nodes, all of the servers which are currently still running, if I go and ask a query, say a reader or writes, is it going to give me an answer? Because a lot of systems, after there's a certain level of failure or network partitions, they're going to stop answering queries because they want to keep that consistency. And then finally, we have partitioning. So that is basically when nodes can't communicate with each other. Now, this could be a glorious network partition spanning the Atlantic. So suddenly your US node can't speak to your London servers. Or it could be something as mundane as one of your servers in your data center is overloaded or garbage collecting, and it's not going to respond. It doesn't really matter why they can't communicate. It's not just problems with the network. And if you start to think about the existing architecture you've talked, we can use these terms to try to describe when you have to trade one versus the other. So if you think of a sharded system, do you get linearizable consistency? Now, if we forget about sharding for now and we just have master-slave, can we get linearizable consistency? Well, the answer is usually yes, because all of your writes are going through a single point. If you're going to want to know a defined order of updates to your data, then yeah, master-slave is really good for you. That's not to say that a lot of the technologies in the NoSQL space that use a master-slave architecture can actually achieve linearizable consistency. Sometimes they certainly don't. And then you have to think to yourself, oh, will my master-slave, is it available? And the answer really is no, because as soon as your master begins to fail, you've got this leader election process, you've got your failure detector, and at that time, if you go to the nodes that are still up, so the slaves or the slave becoming master, they will actually reject your queries. They can't do the query yet. And it's because the ramifications of having two masters is so bad. Everything is fine as long as you don't have two masters unaware of each other. So they're inherently not available systems. Are they partition tolerant? Let's have a think about that. Well, I would say as long as it's asynchronous replication between the master and the slaves, they are partition tolerant. You can handle partitions between the master and the slaves as long as you don't wait for acknowledgements for reads and writes. Then what about for sharding? Well, that depends again on how you've designed your system or how the database is designed. If you've got any global invariants across the shards, so any unique constraints, any types of joins, you're not really partition tolerant, because as soon as you lose communication between the shards, then you can't answer the query. But if you only have local invariants, so you assign IDs just for that shard, you only do queries for the data in that shard, then you are partition tolerant. And so that's why I still think CAP theorem is useful to discuss when we're talking about databases. You just probably can't say MySQL is CP, Cassandra is AP. You need to see how people are using them and what settings they've got. But we haven't mentioned Cassandra too much yet, so it's time to switch gears and to forget all about master-slave and sharding and all of these things we're used to as application developers, using relational databases and using a lot of the NoSQL databases that scale in the same way, and start to talk about a different way of doing it. And it's going to be where we're trading off consistency for availability. So the different way is essentially we're going to allow every single server in our infrastructure, in our database, to handle reads and writes for any value. Does that sound like a good idea? Are you trying to think how you would try and engineer a database like that? When I first read about this, I actually thought it was mayhem. Thought to myself, oh, this is crazy. Imagine I'm updating a customer record on the node in the bottom left here, and at the same time that customer record is being updated in the top right. What do I do? Like, what am I going to do? I'm going to conflict. I might lose writes and all sorts of crazy things. So this, unless you design this very well, it doesn't work. But how all of these systems basically work, or certainly Cassandra, is what we need are a few things. We need a conflict strategy. So we need to be able to either have a conflict strategy for when two people update the same value, or we need to be able to model our data immutably. So like when you're doing multi-threaded programming in Java, you tend to use immutable objects, so you don't have to worry about updates. That's exactly what we're going to do in a distributed system when we're going to have updates from multiple places. Stop thinking about putting mutable state in your database. Start thinking about immutable event logs. like the customer bought this, the customer bought this, the customer bought this, not maintaining a mutable list of all the things the customer had bought. The next thing we actually need to do is a deterministic way of working out where the data really is. Because we're not going to fully replicate the data. We're not going to have all the data on every single node. So we need a way that any node in the cluster, without a master or some special node, can work out where it's actually sending the writes and where it's getting the reads from. And most systems that work in this way are based off this paper. So if you haven't read this paper, I definitely recommend you do. It is the Dynamo paper by Amazon. Don't confuse it with DynamoDB, which is the database as a service offered inside the Amazon cloud. This came way before. DynamoDB was a system built after. And what it does is it describes a way where you want to pick availability over consistency and how to design a database. And it was for the Amazon basket service, because not surprisingly, Amazon realized that they didn't make a huge amount of money when you as a customer could not add things to their basket. And they would rather make a mistake, they would rather accidentally lose something from the basket or add two things to the basket than have downtime. You know, a customer who loses something from his basket will just go back and buy it, maybe. A customer that ends up with two things in the basket and accidentally buys them will get a nice refund and a nice apology from Amazon. This actually has happened to me as well. I ended up with two Kindles in my basket and I nearly bought them. But the idea is that availability is going to be more important, and the odd mistake they will rectify later. And it's not too big a paper, but we're going to go through a number of the parts. Cassandra was heavily influenced by Dynamo. It was also heavily influenced by a paper called Big Table from Google, which we'll see when we get to the data modeling section. And Cassandra didn't implement all of the features of Dynamo exactly like described in the paper, and it also missed a few parts out. So the things we're going to talk about, because what I really want at the end of this talk is for all of you to really understand how Cassandra works, not just what it's good for. Because I assume most people on the call are engineers, are software developers, are ops people, and they like understanding how things work. So we're going to talk about consistent hashing. And this is the way that Dynamo-based databases distribute data across many servers in a deterministic way. The next is replication, and we're going to talk very specifically about topology-aware replication. So Cassandra doesn't just pick 3 random nodes to put your data on. It does it based off the topology of your servers. And with that, I mean, what rack are they in? What data center are they in? Are they likely to have a partition between them? Are they likely to fail together? Do they have the same ISP? You know, do they have the same power supply? Next is gossip. We won't spend too much time on this, but it's an active area of research still. But essentially, if you've got a distributed system, what you need to do is keep track of which nodes are involved, which ones are alive, etc. So gossip is a way of nodes communicating with each other and the information, and basically trying to work out who's there and what their state is. And this is used for 2 things in Cassandra. It's used for the membership ring, so to work out which servers are involved in the database cluster, and it's used for failure detection, so working out when nodes are down and when to just give up on them. The final 2 are about just the realities of running a large distributed system. So if you're going to spread all of your data across many, many servers, at some point they're going to diverge. There's going to be differences. If a node is down for half an hour, or it's partitioned due to a network problem, or it's overloaded, it's going to miss some writes. So we need ways of basically bringing it back into consistency with the rest of the cluster. Now, there are 2 parts of this paper that if you read, you need to ignore if you're just trying to understand how Cassandra works. The first is the fact that it was a key value store. So it was for the basket service. That's inherently a key value problem. It's customer ID and it's basket. And the second part was vector clocks. That is how Dynamo discusses doing conflict resolution. And that was because, as a key value store, if you end up having a conflict, then your entire value is conflicted. You need to work that out and then resolve it in your application. However, in Cassandra, we lean towards actually modeling things immutably and never updating the same field. If that doesn't make sense to you, hopefully it will when we get to the data modeling section. So most of the time in Cassandra, we're never actually going to update the same field, so we're never going to get a distributed conflict. We're basically avoiding distributed mutable state. So onto how we distribute the data. How do we distribute it when we don't have a master telling us what to do? Well, I imagine that a lot of people listening have had a relational database in production, and they've eventually done a query which just hangs. And it's doing some very large table scan on a table and probably hurting the performance of the rest of the queries going on. You're just hoping that you haven't taken down production. And this is bad on a large server, a single server database. It would be catastrophic on a 1,000-node cluster. And we're not exaggerating there. You know, people run 1,000-node Cassandra clusters, though people also run 3-node Cassandra clusters, so it varies. So what we want is a deterministic way to locate our data in the cluster. And that's what we use consistent hashing for. So let's see an example to see how that works. So here's some example data. We have some people, Jim, Carol, Johnny, and Susie, and we have some data associated with them. This is a type of data which you may save in a relational database, but we're going to see how it would be saved in a Cassandra database. So for Jim, we have a couple of extra values. We've got age is 36, car Ford. So you can start to think about the Cassandra data model, and this comes from Google Bigtable, as a map of maps. The first key is Jim, and the second key is age, and then the value being 36. So this is like a multi-map, or it's like in the Java Collections API, it would be a map of string to some value. And Cassandra is a very schema-orientated database. We have lots of types, which we'll see. But what we do is we designate that first key, the Jim, the Carol, the Johnny, the Susie, to be the partition key. And that partition key is hashed, which is why it's called consistent hashing. It's pluggable. You can use different hashing algorithms. The default out of the box is going to be Murmur3. Each node in a Cassandra cluster, each server that you give to Cassandra to use, owns a range. So in reality, this is a huge, huge number. It is either a 60, depending on the hashing algorithm, it could be a 64-bit number, it could be a 128-bit number. We're talking about numbers that are greater than the number of atoms in the universe. However, just for an easy example, let's have a look at how we do it if the hash range was between 0 and 999. Well, what we can do is we can give node A a range of it. So we can give node A 0 to 249, or node B 250 to 499. This is the simplest way of doing it, where each node owns a single range. In reality, in modern Cassandra clusters, we actually give them lots of little ranges, and we'll talk about that when we come to scaling. You'll often see Cassandra and Dynamo-based databases depicted with a picture, and this is why. So you can arrange the nodes in order based on the ranges they own, and you can work out exactly where the data is. So you could go to node D, and he can work out, based on the row that you're trying to read or write, where the data will actually be. So anyone can kind of work this out, and it's not just the Cassandra nodes that can do it. You can go to every node in a Cassandra cluster and ask for any key or any value. However, what you typically do is the driver is executing the same algorithm as the server nodes would. So the drivers go directly to the correct node in the cluster. And you can imagine how a Cassandra node or your Cassandra driver can kind of work out this table in its head. You can see that because Johnny hashed to 50, we know that we need to go to node A to actually get the data. It means it doesn't really matter which node you go to, and it's deterministic. But if we were to stop there, would we be a great database? Would we be any better than when we had a single server? And for me, the answer is probably no. Because what would happen to poor Johnny if node A went down? We would lose the data. Or if he went down temporarily, we would lose availability. If he went down permanently, we would actually lose poor old Johnny's data. So the next thing, and the next part of the Dynamo architecture, and Cassandra has a slightly different take on this than the Dynamo paper, is how replication works. And this is topology-aware replication. But before we go into the details of that, think to yourself, if you've got a database and you take a backup of that database, do you put the backup on the same machine, on the same, say, hard drive as your database? I'd hope the answer would be no. Would you put it on another server? Hopefully, yes. Would you put it on a server in the same rack in your data center? Probably not. Again, racks in data centers often have the same switch, they have the same power supply. You might lose all of the nodes in a rack at the same time. Would you even put it in the same data center? Well, maybe you would, maybe you wouldn't. Depends on how paranoid you are. And if that makes sense to you, then everything Cassandra does with regards to replication will make sense to you. And if you want to be tolerant to failures and network partitions, you have to do the replication based off the topology of the network. So what Cassandra does is it's aware of for every node in a cluster, its rack in your data center and the data center itself. And if you ask for a replication factor of 3, so you want 3 replicas of your data, and that's tunable, you get to pick that. But by far the most common is 3. Then what Cassandra will do is it will make sure that those replicas exist on different racks. It will hash it to get the first one, then walk around the ring until it finds nodes on different racks. So we can work out the primary replica and also the additional replicas by following that same algorithm. We hash it, we walk the ring. And this is really quite different to most databases. Not many databases do this type of replication. If you're working in something like Amazon or Google Compute Engine, then Cassandra is aware of how these infrastructures work, and it will treat a data center as a region in Amazon and a rack as a availability zone. So if you're deployed in EU West and you want 3 replicas, it would put a copy of your data in every single availability zone inside that region. So what would you end up with then? Well, you'd end up with the ability to handle network partitions between the availability zones or racks in your data center. You would end up with the ability to handle 2 full racks going down without having any downtime, which is kind of awesome. With all that said and done, though, we end up actually with quite a complicated write path. So hopefully the animation comes through in time, but this is how a write works in Cassandra. So you as a client, your driver that you're using, which is also open source, basically does that algorithm and picks a replica. Doesn't matter which one, it will be either the primary one, which it has to, or one of the other 2. Every single write, you actually specify the consistency level. We're gonna go with 1 here, which unsurprisingly means that we want to get it to at least 1 node before we respond. Before we tell the client that this write is complete. And because this node that we already spoke to, which I'm going to call the coordinator, is a replica for this piece of data, then this is going to return right away. Already done. We've already achieved the consistency that you want. Now, what goes on in the background asynchronously is the full replication. Now, this happens the same way regardless of the consistency that you pick. So this node will execute that same algorithm, replicate the data out inside the local data center. Now, I'm assuming here that we have another data center inside our Cassandra cluster, and we want to replicate it 3 times per data center. So what the coordinator does is it replicates that over, and it does it once. It assumes that the network link between the 2 data centers is either slower or more expensive, so it doesn't copy it over 3 times. It copies it over once, and that remote coordinator will then achieve the replication within that data center. And at that point, we have a fully replicated write. And this should start to get you thinking how Cassandra differs from a lot of databases. There was no master. We could have used any node as the coordinator. Ideally, we would use one which owned the data. If that coordinator were to fail, the drive would have flipped over and used a different one. If the client had lost connectivity to that coordinator due to some kind of network issue, it would just pick a different one. The only kind of little tweaking knob that you have is the consistency level. And we'll see how that works, but before we do, I just want to absolutely reiterate to people that there are no special nodes in a Cassandra cluster. Now that coordinator was just dealing with 1 request. The primary replica, the thing which is hashed to, that doesn't need to be up for a write or a read to happen. A client driver or an additional coordinator will happily just use one of the other replicas. Actually, it's often based off the latency, how quickly the nodes are responding. So Cassandra has no master. Ops guys, you can reboot the nodes at will. You can reboot entire racks at will. But the one thing you have to decide, and this is where we're going to push some complexity back to the application developer, is the consistency. How long do we need to wait for a write to happen? And what we're going to do here is we get a few different choices. So we could say all. What all means is that we want to get it to all 6 replicas. So in that example, we had 3 in each data center, so 6 total. Or we could say quorum. So we could want to get it to a majority, so that's 4 out of 6. We could do local quorum. Now, local consistencies in Cassandra are really important because sometimes you want to avoid that slow network hop over to the other data center. So you just want to talk to at least 2 nodes in your local data center, so 2 out of 3. This means that if you read and write at local quorum and you always connect to the same data center, then you're always going to read your own writes. Another talk here is again by Christos from Netflix, who actually they talk about the testing they do because they're running across all of the regions of Amazon, so they constantly test how long it actually takes, even if they write at consistency level 1, how long it takes for the data to actually be readable on the other side of the world. I hope you're beginning to realize that all of this makes Cassandra drivers quite complex. So you never put a load balancer in between a Cassandra node and a Cassandra cluster because it's going to load balance requests, reads and writes based off where the data lives in the cluster. You don't want to stick an unaware load balancer in between. It can also do it based off the latency, or you can tell it to only talk to one data center, which means that you only hop over to the other data center if for some bizarre reason all of the nodes are dead in your local data center. So the last thing I want to talk about before we talk about data modeling, is how Cassandra handles additional nodes being added to the cluster. So you've imagined this ring in your head, and this is used to decide where data belongs. The drivers are doing this. The nodes in the cluster are doing this. Well, what happens when we add additional nodes? Well, as I kind of alluded to, each node does not normally own a single range. It actually owns lots of little ranges, lots of tiny little ones, and well, not necessarily tiny. And when a new node joins the cluster, it asks for data. It gets assigned lots of little ranges, which means it can stream data from large numbers of nodes inside your cluster, which means you can bootstrap nodes pretty quickly. It will normally be network bound. While this streaming is happening, then the existing nodes are still servicing the reads and writes. Only when that node is complete and has completed its streaming, that it registers itself to actually join the ring and service reads and writes. And the communication protocol between the Cassandra driver and the nodes is a 2-way chatty protocol, which basically gets alerted when new nodes join the cluster, so clients can start to redirect their requests to the new nodes. So the last section in the Cassandra deep dive is data modeling. Now, we could have spent much longer talking about Cassandra architecture, but I'm assuming a lot of people on the call are Java developers, so we're gonna race through that before we put an end to things. And hopefully you've got the main point that you really need to denormalize. Okay, you can't continue to do joins. We can't have these global invariants around our cluster, which of course could scare you, and it certainly scared me when I moved into these types of systems. I'd been taught for a long time how to do denormalization and to go to normalization, how to go to third normal forms so I can do ad hoc querying. I then later learned that that only scales to a certain degree. And it's pretty simple why, right? If you've spread your data across many servers and you try to do a query which is going to go to all of those servers to answer, it's going to be slow. And it's going to get slower and slower the more servers you add. So Cassandra basically makes you model your data inside exactly how you're going to query it. Once you've got that in your head and you're used to doing that, like the mechanism that you as an application developer actually do it is really easy because it looks just like SQL. Rather than schemas, you're going to have key spaces, which are just made up of tables. You know, you're not going to be shocked to have a look at some of the syntax of SQL, the Cassandra query language. The big difference is that the where clause in your selects are going to limit you greatly. They are not going to let you do all the things which they allow you to do. It's only going to let you do things which go to one node to answer it, or a very small number of nodes. The types you also get, you're not just going to get your normal types, you're going to get really funny types, which you would not expect to see in a database. Not expecting you to read all of these, but have a look at some interesting ones like lists and sets and maps. These are going to encourage you to denormalize, to store all the data in a table and only need to go to one table to read it. The other thing you're going to do is stop using things like auto-increment. And if you put your database developer hat on, you'll understand quickly why. If we've got a 100-node Cassandra cluster, how would you decide the next value for a sequence number? You'd have to go to every single node in the cluster. So you're going to use UUIDs, universally unique IDs, to identify your rows rather than integers. The collections are going to really help you out, and it's really common to put user-defined types inside collections. And a user-defined type is simply you can actually define your own structures inside Cassandra. So here, rather than store a link to another table which has my addresses in, if a user can have multiple addresses, we can create a type in SQL, and then we can actually have a collection, like a set of addresses, or perhaps a map of addresses if we wanted to give each one a queryable name. That doesn't really describe exactly how Cassandra is a columnar store, a wide row store. Cassandra isn't a key value store, and it's not a relational store. So the last thing we're going to do is race through how that works. So here's an example table storing some weather data. We have a primary key. We're used to having primary keys as developers. The big difference, and what you're going to have to change your mindset for, is how you structure a primary key. Because how you structure it will dictate how you can query it. Here, to make something unique, we've done a weather station, we've done a year, month, day, and hour. And if we look at that primary key, the first part is the partition key. So remember back to the hashing, that's the bit that's hashed. Everything with the same weather station ID will end up on the same node, which means that you're going to be able to do really quick queries as long as you include the weather station ID. The next thing that we're going to include is the year, month, day, and hour. Now these are called the clustering columns. These actually dictate the order at which Cassandra stores information on disk. So we're actually going to store stuff on disk on order based off the date, which means we can do really quick range queries. And when we put all that together, regardless of the size of our Cassandra cluster, we get to go to a single node, assuming we use the partition key. And then we can start to do range queries on the clustering columns. And this is great because it allows us to be sympathetic to the hardware. We get to read disk sequentially. So if we were going to do this query, what Cassandra would do is it would go directly to the partition key. We know which node that's on. It's then going to do a single seek on disk to get your data. And then it's going to turn it into a nice table just for you. So you don't need to think about this from an application development point of view. You're going to get tables just like you got tables in a a JDBC-based driver. But you are going to get better performance because it's stored nicely on disk for you. So you really need to think about it when designing your primary key. Now, an extra section I was going to go through if we had time, which I don't think we do, was actually looking at some Cassandra code. Actually look at some Java driver code. I'm going to skip that because it looks virtually like JDBC. There's nothing exciting about the code which looks at. You can have prepared statements, you can do queries, you're going to be able to do exactly the same thing as you do with JDBC. The difference is how you model it. You're not going to be able to do joins, etc. So I'm going to skip this section and run through, but I'm going to provide the slides later so you can have a look at it and go kind of take a step back and summarize the things that we've spoken about. So the first point I'm going to make, if you're going to use a database like Cassandra, which differs a great deal from your relational databases and most of the other NoSQL databases, you need to take a step back and realize, do you actually need to? Does your problem fit on a single computer? If it fits on a single computer and you can handle some downtime when that computer is rebooted or patched or sets on fire or a tornado hits it, then I would definitely suggest still using Postgres. But if your problem is greater, if your data set doesn't fit on a single computer, if you really can't handle downtime, then definitely look at Dynamo-based databases. I think Cassandra is pretty much the leader in this space. So it's a really cool technology to work with, and it's got lots of open active committers which you can go and communicate with an IRC, etc. But yeah, use the right tool for the job. So on that point, I'm going to say thanks for listening. if you've got questions now, I've got time, though I realize we're running out. We did start a few minutes late, but we are running out of time. If you've got questions later, feel free to ping me on Twitter. If you've got any feedback for me, because I always like feedback and improving presenting, then feel free to drop me an email. Or if your question just happens to be more characters than fits in a tweet, feel free to drop me one there. I also blog a lot about Cassandra and new features that are coming, etc. And also generally about fault-tolerant software and handling failures and what developers should know about networks and these things. So if you're interested in that, then feel free to read my blog. But on that note, I will open up for any questions.
Okay, awesome. So thanks very much, Chris. So yeah, if anyone's got any questions, please feel free to put them in IRC. I've literally just pinged people that text as well. Quick question from me, actually, Chris. You mentioned obviously data is going to be stored on different nodes, and you mentioned that does restrict the usage of a where clause on CQL.
Correct.
How does that actually in real life, in reality, how does that actually affect developers? Is there something they need to do in the design of their code, or is it more down to the design of?
Correct. If we'd spent a full hour kind of talking about how to model data in Cassandra, like rather than Cassandra's like architecture, what we'd have talked about is we would duplicate data many different ways with different primary keys. So we'd be able to query the same data many ways. This is something you have to do manually at the moment in Cassandra. So in Cassandra 3, which will hopefully be released sometime this year, there's a feature called materialized views. And what these are essentially going to do is you say, I want to store this data, but I actually want to use multiple different primary keys to store it. So I can query in each of those ways. And then Cassandra will handle the duplicating and when you update the main table, it updates your other views, etc. So it's going to make it a lot easier for application developers.
Okay, so a lot of the time with like joins and things like that, you have to maybe even do it yourselves rather than.
Ideally, rather than joining, this is another good question. What you would do is rather than store the entities in two separate tables, you would make it a single table. If it was like a one-to-one, you would end up just putting the data there. If it was a one-to-many, you can use a set or a map or a list. If it's a many-to-many, you're probably saving it completely two different ways.
Is that the right way of? I mean, you mentioned Cassandra's perhaps maybe fixing this. If we do call it a bug, I don't know. Maybe it's a design issue or something. But, I mean, is that the right way to do it? I mean, because wouldn't you end up with like huge tables of
Correct, but if you're running Oracle or you're running MySQL or something, your storage is probably a very expensive SAN, some very high enterprise disks, heavily rated. Whereas in Cassandra, you're typically using commodity hardware. You're definitely not using a SAN because they're actually quite terrible for database performance. So even though you're storing your data multiple times, it can often be cheaper because you're storing it on lots of cheap commodity disks rather than expensive storage. Like SANs cost millions. But it's another little point there, though, is if you actually try and scale a relational database, nearly everything you do, like you start to remove constraints, you actually do start to denormalize if you want to scale it and increase your read and write throughput. Basically, Cassandra forces you to do that from the start so it scales. So you can always go to one server to get the response.
Cool. So one question has come in from IRC from MW. Can you recommend any additional literature on Cassandra? So I'm guessing books or docs online for that.
There are a number of Cassandra books. There is only one really good one, and that's called Cassandra for High Availability. It's written by a guy who has written applications with Cassandra for a long, long time. The other thing you can do is go to DataStax Academy. This is a free service that will both educate you about Apache Cassandra. It can be even free instructor-led training or self-paced, a bit like Coursera, I guess, if people have used that. So you can do whole courses. I'm often hesitant against, if you read blogs, which are great for solving a particular problem, just make sure they're pretty up to date because the older APIs for Cassandra, it's completely changed. If you see the word thrift, run away. Look for SQL.
So that's Cassandra High Availability. Is that by Robbie Strickland?
Absolutely, yeah.
Okay, so I'll paste that into the IRC now. Snazzy also mentions planetcassandra.org.
Yeah, Planet Cassandra is another good one. Planet Cassandra is really good if you want to see use cases from lots of people you'll recognize, like Netflix, Spotify. There's all sorts on there. So if that's got a lot of the use cases, it's also got some tutorials. The docs produced by DataStax are pretty good as well.
Yeah, Snazzy just put the academy.datastacks.com in there as well. Do you want to mention DataStax a little bit and say what they do, how they use Cassandra?
Absolutely. So DataStax, we build a product on top of Cassandra. So if Cassandra sucks, our product sucks, which is why we put so many people at DataStax commit to open source Cassandra, and why people like me talk about it a lot. What we were not like a lot of open source companies, which we just charge for support on top of Cassandra. Our product actually has additional features which are closed source. So tight integration with Apache Spark. So if people have used Apache Spark, it actually embeds the worker in the same JVM. Tight integration with Solr, so you can actually do text and like Lucene-based queries on your data in Cassandra. And then you do get support, and you have operational things like for provisioning clusters, etc.
Cool. One question in from I think it's Jekko in IRC. have you used TitanDB, the graph database that has been acquired by DataStax, and when would you use it instead of Cassandra?
So TitanDB, and he's right. There's a company called Aurelius, which DataStax bought. TitanDB was a graph database, but it didn't handle the storage. So you actually use Cassandra when you use TitanDB, or you use HBase, or you use, I believe it's BerkeleyDB. So it depends whether you want to model your data as graph. I mean, obviously the reason DataStax bought Aurelius was to add graph support directly to our product.
Okay, so it's really just a different modeling kind of view for your data.
Yeah, if you look at most graph databases, they nearly all only vertically scale. It's a really hard problem because graph databases imply you really want to do the absolute of ad hoc querying. You want to follow many relationships, which if you've separated your entities across hundreds of servers, following those relationships can be quite expensive and slow.
Okay, so I think we are entirely out of questions on IRC. So yeah, that leaves me to say thank you very much, Chris, for your hopefully first of many sessions on the virtual jug. That was a great session. Thank you. Any questions or final points, Oleg?
I don't think so. So it was a great session.
Looks dark in Estonia right now, Oleg.
No, I'm
very hard in IRC is a Cassandra committer.
Ah, right, okay.
Okay, yeah. So it was a great session. I enjoyed this a lot. I don't have any questions on the subject, but I would love to chat with you, Christopher, at an interview for Rebel Labs.
Sounds good.
Yeah. So next up, we've got an interview with Christopher, as Oleg mentions, and that's going to be available on the Rebel Labs site, so 010round.com/Rebel Labs, where there's a whole load of tech content as well as Rebel Labs write-ups of VJug sessions, and that'll be up hopefully this week, and we'll also include the interview with Cassandra, so we'll hear exactly what makes Christopher tick. So yeah, big thanks again to Christopher, and in fact we mentioned graph databases. Let me share my screen again very quickly. We mentioned graph databases. Can you see my screen?
Yeah.
Cool. So the next session actually is about graph databases. So this is actually the month of data really. On the 28th of July, same place, same time, we have value in relationships: how graphs make databases fun again. And this is from Michael Hunger, who works for Neo4j, and stop screen sharing now. There we go. So yeah, Michael works with Neo4j, and he's going to give us a great session as well on graph databases. So yeah, it leaves me to thank you very much to everyone who joined. Thank you for your questions, and see you next time on the 28th. Big thanks again, Chris.
Goodbye.
Thank you. Bye bye.